All right, so I was meaning to record this video mainly on the day that I solved it, but this genuinely might be the most troll problem ever. I'm gonna call this the hardest, easiest problem ever that I've solved, at least in recent memory. I'm sure I've solved a maybe more troll problem, but this question is really just dumb. I think it's just a dumb problem, and it's just funny because it's just I I was one of those people. If you did this problem that were struggling on it, and then you realize you struggle for it for 90%, you're like, how do I code this? I don't like it, I don't like it. And then you realize that dog, it's not that deep, it's really not that serious, nah. And if you don't believe me, so I'm going to read the question out, and then I'm going to show you my it's the this even if you don't do coding, I just want you to be like, wait, what? It's that simple? Just trust me. All right, so you have an array, and it's a simple problem statement. You can choose any element in this array and then increment it by one. Once you do that, you move that element to the back. That's how you gotta do. And you can do however many operations you want, but the problem is you want to find the lexicographically smallest array. What lexicographic means is just if you have a bunch of strings, you want to sort those strings in alphabetical order, right? So if the first characters of two strings are the same, then the second, then the third, you find the first character in which they differ, and then you compare that character, and whichever one is alphabetically smaller, that's a lexicographically minimum one. Or if they don't have any characters that differ, but one is shorter, then that's lexicographically smaller. So it's just a very simple compared to, which is now synonymous to what lexicographic means. Okay, so now that you understand that, we basically have this array, and we want to, you know, make it lexicographically minimal. And so, so you might be saying okay, well, the first intuition that you would have, the first thing that should come to your mind is just okay, wherever the minimum element, because I know that I can make these elements smaller. Obviously, this operation is not making any of these elements smaller. So wherever the minimum element is, I need that element to be in the front of my array, non-negotiably. I don't care about what happens. That needs to be the first thing that happens. That's my priority. And so now you realize, you start coding, you might start thinking about it, and you're like, damn, this is low-key a little tough, bro. And this is a problem D on a Codeforces. All right, let me just tell you that this is div 2D, so this is intermediate coding. Unless you're not some genius, this is probably the types of problems you'll be solving year 2 or year 3 in your coding journey. All right, like a div 2D. Now I give you an asterisk on this because it is a 1600. Div 2Ds are usually harder than this, but 1600 would be more like a moderately difficult problem C. A easier C is probably 1200 to 1400. A moderately difficult C is probably 1500 to 1600. And then a hard C is 1700 to even 1900. And then 2000, you won't see that. You'll see that every blue moon, though. So this is still a generally difficult problem, and this question looks like it's 1,000. Let me look at my solution. This literally looks like it's an 1,000 problem. Okay, sure, you're using a priority queue, but it's not like you implemented a heap. A priority queue, the usage is all just saying, okay, can I find some data structure that can query the minimum element in log n time, and then remove it in log n time. So it's not that serious, right? And this is literally the solution. I'll explain the logic, but I want to show you, y'all were probably struggling a little bit on the solution, and now all you did, my dog, was you had a priority queue, and you added the element, the value of the array, and the index. And then once you did that, you just populated the priority queue. It's very normal stuff. And then, I kid you not, the main solution is this long. Okay, I'm not hacking into Codeforces, and I kid you not, it is this long. It's find I'll explain the logic later, but it's just remove from the priority queue, check if this value is greater than or equal to this value. If not, print this. Else, add that. And adding it is not some complicated math. Dog, I added one. I added one, my guy. No, I genuinely just added one. I didn't do P0 plus n choose k minus k factorial to the k e log n, bro. No, I added 1. That's all I did. So it's like, bro, what the heck? Yeah, this is a what the heck problem because it's very troll. So now, I'm not trying to like get, all theoretical here. I'm just trying to show you this is a very troll problem because I'm going to just tell you the solution really quickly and you're going to be like, oh, damn. So in this problem, right, for these types of problems, in my opinion, when you're trying to construct like an array, it's really good to work on examples. Like examples will give you insight. Don't work like generally. Don't like write A1, A2. No, you need to see concrete values. So that's just like obvious in my opinion. So this test case gives you a lot of insight because basically what's happening here is think about it like this. If I want the lexicographically smallest array, the only element that is on my mind right now is the minimum element. That element must be in front. So I see that 1 is the minimum element and it's already on the front, so I'm good. Now I'm thinking about the next minimum element. It occurs over here. This guy needs to be in the front of my array. I don't care what happens. That guy needs to be in the front of my array. And so what I do is now, because I said, now notice what I'm doing. I jumped from this minimum to that minimum. So what I'm doing is I'm basically querying um, the minimum element in the array. But then if any two are the same value, if there's more than one minimum, then I break the tie with with the index. So this is index 0 and this is index 3. So basically, I'm finding the leftmost minimum. That's what I'm currying, right? So if I'm currying the leftmost minimum, right? Because you in these like implementation types of problems, you also need to understand like what you're doing, and so I'm currying the leftmost minimum, right? Right? Because all I'm saying is that like I'm thinking about, and it makes sense because I only care about the minimum element, and once I curry 1, I'm saying okay, well this element needs to be in the front. If so, it is very possible for this element to be in the front. Like I'm gonna once I query this minimum, I'm gonna print it out. So in my string, so this is my string or something. But then this guy, I'm gonna also print it out. But notice that this element, these two elements, or they need to be incremented by 1 and move to the back. And you might be saying, well, ooh, should I worry about that right now? No, just print out 1. Like, okay, so print out 1, and here's a tip, right? A lot of times when you do an operation, you might worry about like, oh shoot, well then it caused this to like, you know like to like you're focusing too much on like the ramifications. No, at this moment of time, you've done exactly what you've needed to do. You've printed out the second one because you know that 1 has to be after the first one because we want the lexicographically minimal 1. So you've printed out 1. So now focus. Don't worry about, if you had 1 and you had all these elements here, bro, you already know it's not feasible to worry about X, Y, Z, A, B, C, D, E. It's not feasible to worry about all these elements and moving to the back. So don't. So don't, right? Because obviously, then such a solution would probably not worry about that. So then I'm not going to worry about those twos, but I do realize that those twos do need to be incremented. But like, let's just say, let's just think about this. Now I need to query. Um, Now I'm currying the leftmost minimum. That element that has to be the next element that gets printed out, right? But now think about it. The leftmost minimum here is this dog right there. It's this dog right there. And so think about it like this. When I query the leftmost minimum, basically what I'm doing is I have a I populate a priority queue with value and index. And the idea here is that like when I query this 2 1, right? I know that because the previous index that I printed out, because that dog is greater than or equal to the current index that I have, and the current index is this, because that pair that I queried occurs before the previous one, then in order for the previous one to have been printed out, in order for this one to have been printed out, then it's obvious that this element, this value, had to have been incremented. And if it's incremented, we say, so this is a fraudulent pair. This pair doesn't exist anymore because we know that that has to have been incremented in order for that one to have had been printed out. And so it's, since it's fraudulent, right, I'm going to remove that from the priority queue, right? So if this is the case, right, then remove the fraudulent pair, remove the current index or the current value, and then comma the current index. So I'm gonna just say, I'm gonna write CV current value, remove current value and current index, right? It's a fraudulent thing, but then I need to replace it to what actually exists. What actually exists is that you have 3, and you're gonna move this guy to the back. Look, I don't know where it's gonna be in the back, but the idea here is because I need to, because when I'm currying a minimum, I need to when I'm currying a minimum, I have the current index, and I want to see, is it greater than or equal to the previous, or is it less than or equal, is this less than or equal to the previous index? Because I'm doing that to see if I need to, if it's a fraudulent pair, then what I need to make sure is that when I remove this guy, this 2-1, because I know it doesn't actually exist, it should have been incremented, moved to the back, I'm gonna just replace it with the index n. And the reason why I'm going to replace it with the index n is because I need to make sure that when I add this pair back, it has a greater index than every existing pair. Because my claim is that right now, every existing pair is not a fraudulent pair. It is actually a genuine pair. And if it's not a fraudulent pair, I need to make sure that this pair has a greater index than all of those pairs. And because they occur, because this 2 is going to be pushed back to this 2 is going to be to the back of my array, which means that its index has to surpass, like, dog, you can't, when you move stuff to the back, that means its index surpasses the index of every pair that's in my priority queue. How do I represent that, my dog? My dog, I just say, let it be n. Let it be n. I don't know what it is exactly, but just let it be n. And so I'm going to add this guy to my priority queue. So then remove this and add CV plus 1, and then CI, or then N. Once I add that, okay, I'm gonna, now let's say this, right? Let's say I query an element that is AN, right? So here, I'm gonna remove, I'm gonna put 3 and then comma 0, 1, 2, 3, 4, 5. There's 5 elements, right? 3, 5, and then I'm gonna query this again. When I query this again, I know that 3 is or the leftmost minimum here is gonna be 2, but then I know that the previous index was n, and that's obviously greater than or equal to my current index, which means that in order for me to have printed that, um, that had to be moved to the back. So what I'm gonna just do is, I'll just print out 3, 3. But really, what's going to happen here is when you query 4, when you query this 4 and you have 4, since the previous index was 5, since the previous index was n, which is 5, that you printed an element that that occurred before you and had to be moved to the back. So what that means is that you have to increment this element to be 5. So that's basically what we're doing. So I know that maybe like that doesn't make sense, but let me show you the solution, right? Right? The mindset is that I only care about my minimum element, right? What I'm gonna do, I'm gonna query the leftmost minimum element, which is what this nonsense is saying. It's saying, okay, so if the values are the same, then sort it by the index, right? By ascending index. Otherwise, right, just you sort it by ascending value, right? If the values are not the same, I sort them by ascending value. And so then what we're gonna do here is we're gonna query the leftmost element, right? And the idea here is that, like, in general, I'm going to print it. The only case in which I'm not going to print this is if the previous index, right? Okay, so um it shouldn't be greater than or equal to. It should be greater than. Okay, that nuance doesn't really matter here. You can figure that out. The reason why I put greater than or equal to is because for previous indices, you know, I allowed some indices to be n. So if you have like n and n, you can print it out. Don't really worry about that. That's a nuance that you can figure it out if when you go and code it. I feel like figuring out nuances make you understand it more. But what I'm basically doing is I'm going to print out that element. And when I print out that element, I'm going to set my previous index, right? And the idea here is that when I carry the next element, the idea is that could I have printed out if the index, right? As long as the index is greater than or equal to the previous index, then I can just print out normally. But if it's not, if it's less than the previous index, um, this means in order for the previous index to have had been printed out, I would have to add one and move that guy to the back, which is what I do when I do this line. So yeah, that's pretty much the solution. Like, yeah, honestly, like, yeah, I guess like the insight here is just like you always want to just think about like, okay, I only care about the minimum element, and when I only care about the minimum element, it might be like when I if it occurs here, I might worry about all these elements that I have to worry about later. But you notice that if you don't get too bogged down by this and you just focus on minimum by minimum by minimum, these elements get resolved either way. And so that's sort of the mindset that you need to have because you know for me, it was like, oh, I gotta get bogged down by all these elements. But no, just print out the minimum, and then print out the minimum, and then you gradually resolve these types of elements that like kind of like screwed over your thinking. But yeah, that's it.